Hello everyone, in this video this is the problem that we will solve. We have a water tank 22 feet in diameter is made from steel plates that are 1 inch thick. Find the maximum height in feet to which the tank may be filled if the circumferential stress is limited to 6,000 psi. The specific weight of water is 62.4 pounds per feet cube, assuming water pressure distribution to be uniform inside the tank. Okay, solution. So in this problem, we will have a tank that has a diameter of 22 feet and a thickness of 1/2 inch. Okay. Now the question is, what should be the maximum height that we can put in the tank so that it will not exceed the circumferential stress of 6,000 psi. Now for this problem, this is considered to be a thin-walled vessel due to the proportion of the diameter and the thickness. The thickness is very small compared to the diameter, which you can determine the specific ratio in our module. So this is under thin-walled vessels, a thin-walled tank. Now, the formula for the circumferential stress of a thin-walled tank or vessel is, we have the pressure times the radius of the tank all over its thickness. Okay. Now we are given with the specific weight of the water, and we are given with diameter, the thickness, and we are given with the limiting circumferential stress. Okay, circumferential stress is 6,000 psi. Okay, first we need to identify how the water affects the tank. Now, with the water level, let's say for a height of h, since that is the question of the problem, the water will apply pressure to the tank sideways. Since we are not concerned for the longitudinal stress, we are only concerned with the circumferential stress. So we will consider the force, the effect of the water that will tend to affect the circumferential stress. So the force of the water will try to move sideways and try to break apart the tank. Now, to bring out the forces that are affecting the tank, let's try and cut the tank along this plane. So we will have the tank, okay, right. So the force of the water will now be moving sideways. Yeah, the force of the water. And now, to prevent the tank from bursting, the circumferential sides of the tank will apply a resisting force, which we can set as letter T. The force of the water and then the resisting tension developed inside the tank. Now this is 2. One we have here for this side. The other one is for this side. Okay, so there are 2. So if we sum up forces, is equal to 0 to make the tank remain balanced. So we will have, assuming the T is positive, so that becomes 2T minus F is equal to 0. Now, how do we relate the T and the F with our given? Let's start with the force of the water. The force of the water, we have, it will come from the specific weight of the water. Now, this statement is very important. Assume water pressure distribution to be uniform inside the tank. What that means that the pressure inside the tank is simply equal to the unit weight of the water multiplied by its height. So whatever is the height of the water, you just multiply the height with its unit weight, then that is the pressure that the water is applying. So basically, this is now the pressure of the water. Okay. Now, if this is pressure, to obtain the force of the water, you need the pressure of the water multiplied by the area wherein the pressure is applied. Okay, to obtain the pressure, that is simply, pressure is also a stress, which is force over area. So to obtain the force of the water, which is F or Fw, you simply multiply the pressure of the water times the area where the water is applied. So in this problem, we have the force of the water, it is applied in this area, which is, we have this area. Now this is the equal to the diameter of the tank. Now, if you notice in the problem, it states here 22 feet in diameter. It did not mention is it an inside or an outside diameter. It simply stated diameter. So for simple purposes, we will not subtract the thickness of the tank. We will directly consider the total diameter as this side. Okay, so actually the pressure of the water will only apply within this area. No, it will not include this small part for thickness, but since it need not mention the diameter is whether inside or outside, so we will consider this entire whole diameter as the area that is where the pressure force of the water is applied. So this is D. Now of course this will now be the height of the water, no? Assuming that is where the height of the water is, or how high the water is. So the area is simply this surface, which is D times H. So the area is D times H, no? The area for the water. So that is, the area of the water is D times H. So substituting it here, we have 2T minus pressure of the water times the height is equal to 0, or we have 2T is minus, we have the pressure of the water is the unit weight of the water times the height times wait, we have the force. The force is the pressure of the water times the area. Now this is pressure of the water times the area. Pressure of the water times the area, that is force, and the pressure of the water is unit weight of water times height, while the area is the diameter times the height, which is now equal to 0. So notice this is what is asked in the problem H. We need to solve H. That is the question of the problem. We have D. D is 22 feet. We also have the unit weight of water. The unit weight of water is 62.4. So the unit weight of water is 62.4 pounds per feet cube. So we already have the unit weight of water. Next is tension. How do we relate? Now we know stress is simply force over area. So this tension is actually the circumferential stress, or this tension is derived from the circumferential stress. So basically, the circumferential stress is equal to the tension developed in the tank all over the area where the tension is applied. So we already have the circumferential stress, which we are given with 6,000 psi, and we need T. The area now where it is applied is, let's see. Now the T is applied in this in the tank, in this small area, in this small strip. If we draw it here, okay, we draw it there, that is where the T is applied, wherein this is now a height and this is the thickness of the tank. So the area is the height times the thickness. So to solve T is the stress circumferential, times the area T, which is also equal to stress circumferential times the height times the T. Okay, so substituting it here, we have 2 times the T is stress, height times thickness. So we have the circumferential stress times the height times the thickness. Now let's we have it here, transpose this one to the other side. We have unit weight of water times h times the diameter times the height. Okay, we can cancel one of the h. Okay, substituting the values, so this is 2 times 6,000. This is still psi, pounds per square inch. So okay, times the thickness. Thickness is 1/2, so we have it here 0.5 inches. Then we have the unit weight of the water, 62.4. We have 62.4. We also have the diameter is 22 feet. And then we have the height. Okay, so if you notice, we only have one unknown equation. But first, let's check the units. This is pounds per inch squared. This is also inch. This is pounds per feet cube. This is also feet. Okay, so we need to convert either inch to feet or feet to inch. So let's read the problem. Find the maximum height in feet. So we need to change the inches into feet. So we have 2 times 6,000 times in 1 feet there are 12 inches. Then we square this one, okay, times 0.5. This is inches, so you have 1 feet is equal to 12 inches. Then we just copy 62.4 times 22 times h. Okay, so let's simplify these terms first. So 2 times, we have 6,000 times 12 squared. We have 864,000. 64,000 times 0.5 divided by 12. That is, let's just put it there, 1/24. Then we have 62.4 times 22, then this is h. Okay, this is now pounds per feet squared. This is also now in feet, so everything is now in pounds and feet. So rearranging to solve h, we have 2 times 864,000 times 1/24, 62.4 times 22. So transferring this 2 to the other side, so it will now be divided. Solving for h, we get 2 times 864, 1, 2, 3. What else? Times 1/24. 1/24. And then 62.4 times 22. Yeah. And we have 52.45. So you have 52.45. Yeah, 52. Now let's check what will be the resulting units. You have it here. This is pounds per feet squared. This is in feet. This is also in pounds per feet cube. This is also in feet. So the unit of this one, pounds per feet squared. Unit of this one, feet. unit of this one, pounds per feet cube. The unit of 22 is feet. So we cancel out feet, cancel cube, so this becomes squared. This two has the same unit, we cancel, so only feet is left. So this is now feet. 52.45 feet. That is the maximum height that we can set for the water to not exceed the given circumferential stress.